All right. Welcome back. Happy Friday. I want to go over a new library called Pandas today. But I thought we could check in about how you're feeling about NumPy before we do that. So yeah, how are you feeling about Wednesday's material or NumPy?
I don't know about everybody else, but like this stuff made sense. And like I feel like when I was watching it, I was sort of like taking in a lot of information, but it's probably gonna take some practice before I could actually like just on the spot be like, oh, this is what I should do at this point.
That makes a lot of sense. So I included a bunch of like suggested NumPy exercises at the end of Wednesday's slides. I didn't go over them, but like in class. But if you take a look at the slides, you can see those. One option is we can do some of those in class today, or you can just go right into Pandas. So you could take a look on your own. We could look as a class. What do people want to do? So if we go over them as a class, then it may delay us by a day before we get to like the next piece, but that's okay with me.
Is there I mean, I'm on a more beginning coding level than I think most people in this class, but for me, the most helpful things I've been doing are like the Code Academy classes, where it kind of like talks you through a problem set like a little bit, and that's been really helpful. Is there something like that for NumPy?
Yeah. So let me pull up the let me see what I included here. So well, so there's the one place to start is the material in the in module 4 is from the like Python data science handbook. So that gives some, it's not video based, but it gives some something. Another resource I can point you to is a course, one of my courses, where, let's see, I have to find the NumPy lecture. Yeah, so I can link to this video here. And then I'll give a, yeah, so the YouTube video is like the lecture, and then the second link is the like exercises and like tutorials that you can flip through. There's another link to the NumPy and Pandas like Python data science handbook tutorials. Let's see. I don't know if there's specifically a Code Academy NumPy. Oh yeah, there is. Here's a Code Academy course. I guess so NumPy is a very like it's a huge library. Pandas is also a huge library. You don't need to know all of it. The way that I think is like easiest to get started with NumPy is to just like start using it to manipulate data and like try out different things. So the place that I would recommend starting is not those tutorials. It's just like trying out exercise, like, okay, can you create an array? Can you manipulate the size of it? Like, kind of think through what sorts of things logically might I want to do with a table of numbers. Like, I want to maybe select out a row or a column or a particular subset of it. Maybe I want to reverse it, sort it in a particular way. So those are the sorts of things that are most useful in practice. And then also, like, as we get into actually working with data, you can kind of learn things as we go based on what you need. But trying to learn the full library in one go is, I mean, it may be possible to do that, I'm not sure, but I don't think it's the easiest way to learn this stuff. So I guess my recommended next steps would be either attempt, like, going through the kind of suggested exercises at the end of Wednesday's slides, or we could like work through them as a class, but then we'll be delayed going through Pandas a little bit, but that's fine with me. So I guess if you're feeling, if the consensus is like, you have no idea what NumPys was about, like I was kind of just like talking and nothing was making sense, then it would be good to maybe go through some examples and like make some of that stuff more concrete. If you're feeling like, okay, maybe I sort of got it, but I'm going to need to practice, then maybe practicing on your own would be more efficient. And then we can move on to other material and, yeah, so.
Something I think, like, personally, I feel like would be helpful is like to connect it to like what we're eventually going to be doing with it. Because I think that like coding can kind of be abstract and doing all these like learning NumPy on Wednesday, for instance, like making like these lists and I don't know the exact functions, but arranging stuff and all that. And it's like, okay, like what's actually the situation I'm going to use it in? How does this apply to, yeah, all that helps me, like the process and the connection helps me like remember it better, I guess. So
sure. Yeah. So I have some examples where we can go through like small data sets as part of Pandas. So to give you like a little preview, I can repeat this also when we actually have the slides up, but Pandas is like it's built on NumPy. So NumPy lets you work with these matrices, like 2D tables of numbers. And then Pandas gives us a way of like labeling the rows and columns. And that's usually how we'll actually interact with data in practice. So it's good to have like a sense of how NumPy works under the hood, because a lot of the ideas are kind of translated into Pandas. But the main way that I'm guessing we'll interact with data in this course is with the Pandas library. So one thing we could do is just like move forward with Pandas, see how it's going. If no one's getting it, then we can go back. But I have a few kind of more concrete examples in today's slides, so hopefully that will help. But okay, how does that sound? Got one nod. Okay, multiple nods. Let's see how it goes. Okay. So let me just share my screen. Okay. Okay, so like when we went over NumPy, I think the best way to learn this stuff would be to like open up a collaboratory notebook and you can type things in as we go. And then, let me find the slides. So that you can follow along in case that's useful. So I'll paste this into the chat. Okay. Okay, so that will let you, copy and paste commands so you don't have to retype them. Although you can if you want. Okay. So Python or Pandas is another like fundamental package for doing data science in Python, and it's built on top of NumPy. And Pandas stands for Python Data Analysis, PNDAS. So here are the letters. Okay. The main feature that Pandas introduces are two new data types, and they're called series and data frame. And then Pandas also includes like a wide variety of useful functions for like reading in data and manipulating series and data frames objects, including like some basic stats and plotting tools. Pandas is installed by default in Collaboratory, but if you're not working in Collaboratory, you can install it in other environments using this command here. So using pip install pandas. In order to import pandas into your workspace, I like to use this command. So we can flip over to our Scratchpad. This will make pandas accessible, and I almost always abbreviate pandas with PD. The first pandas data type that is useful to know about is the series object. And you can think of it like a one-dimensional array of indexed data. So depending on how you use it, a series is kind of like a list or a dictionary or a one-dimensional NumPy array. Or maybe a combination of all of them. And here's one way of making a series. So you call it, say, pd.series. And then here we're creating a series using a list object. So this is going to create a series of values with the elements, 0.25, 0.5, 0.75, and 1.0. And then when we print out the series, then you can see it kind of prints out this little table with the values in one column and then kind of numbered rows, and they're 0 indexed by default. The data in a series object is actually a one-dimensional NumPy array, and that's one way that Pandas is built on NumPy. And you can view the NumPy array that's like inside of the series object by using the .values attribute. So if you say data.values, what comes back is a NumPy array with those values in them. And then the labels are stored in the index attribute. And by default, series objects are indexed using what's called a range index that gives each row as an integer, ranging from 0 when it starts to the number of rows minus 1 and in increments of 1. Then you can use slice notation or the square bracket notation for series objects, just like for NumPy arrays. So like data square brackets 2 gives you the third element, because it's 0 index. So this is the 0, 1, 2 element. So it gives you back 0.75. And then you can also select out a range of elements, like the second element to the fourth element, or to one before the fourth element, will give you elements 1 and 2. And this actually returns a new series object where, well, it's not a new object, it's actually the same object. It's called a window into this object that retains the same labels. How's it going so far? Too abstract? Good, following? Okay. Maybe it makes sense, but you don't know why it's important, why it matters. That's maybe as good as we can hope so far. Okay. Unlike NumPy arrays, you can rename the index labels for each item. Here's one way to do that. So you can use this index flag to pass in a bunch of labels for each item. And then that will overwrite the default labels for the items. Instead of labeling them like 0, 1, 2, 3, now the items will be labeled with whatever new thing we passed in. Okay, so when we print out the object, now we have these labels attached to it. And one way that this is useful is we can use a series object as like a more powerful version of a dictionary. So just like a dictionary object, you can refer to specific labeled entries and get out the corresponding values. But then, unlike a dictionary object, you can also look at like a range of values. So if I want like the A entry all the way up to the C entry, I can use slice notation, not on numbers, but now on the labels. So I can get everything from like the A label to the C label. And this will return a new series labeled the same way as before with the corresponding values. All right. Good so far? Not good? All right. Guess I'm going to keep going. Okay. Please do jump in with questions. I can't read your minds here. So, all right.
I actually have a question.
Yes, great.
Is there a way to just do like A and C without getting B?
Yeah. Let's try it. So let's copy this thing here. Okay, so we can print out data. So we can just say A and C. Oh, just kidding. I think you might have to pass in a list. Yes. Yeah, so you can pass in a list of the things you want to get out, and that will give you A and C. And then, like, you know, A through D gives you all of them. If I just want to go like B through D, I can use that. Okay. The second type of kind of object that Pandas introduces is the data frame. And you can think of a data frame as like a more powerful version of NumPy arrays. And the way that it's more powerful is it's got labeled rows and columns. So rows of a data frame are called indices or index. And then the columns are called columns. There are lots of ways to create data frame objects. So probably moving forward in this course, the way you'll most commonly make a data frame is by like reading in data sets from whatever files store the data. And then sometimes you'll end up like piecing together a data frame from multiple sources. But just as like a quick example, we could build up a data frame from scratch using 2 dictionaries. So I'll copy these in to the scratch pad here. So this stores the areas in square miles of 5 states. And then here are the populations, you know, from some year in the past of these 5 states. And then we could create a data frame by using a dictionary where the keys are, so these will become the columns. So population is one column, and the values will be specified by this other dictionary, populations. And what this is going to do is is add the rows that correspond to the keys of this dictionary. And then the values in this column and these rows are going to be given by the values of this dictionary. And then our data frame is going to have a second column called area, and the rows and values are going to be specified by this areas dictionary. So when we print the whole thing out, we get this like nice looking formatted table where the rows are the different states, the columns are given by the keys of the dictionary that we use to create it, and then the entries are given by these dictionaries here. Yeah.
Can you also do that with like multiple series instead of dictionaries?
Yeah, yep, totally. Yep. There are lots and lots of ways to create a data frame. You can also do make a data frame out of a NumPy array. So if you just create a data frame from a NumPy array, by default, it'll label the rows and columns with like the integers 0 through number of rows -1 and 0 through number of columns -1. But that's totally valid. Okay. Oh, yes. And then we can look at the how like the different pieces of this. So states.values is going to be a NumPy array with the actual data in it. So so the type of this thing is an actual NumPy array. And so just like series objects, data frame objects are a wrapper for NumPy arrays. And then we can get out the row labels by saying states.index, so using the index attribute. So in this case, the rows are state names. And so here they are. And then we can get the columns by using the columns attribute. And the columns in this case are population and area, and here they are. So if I wanted like the 4th state, I could use it, index it just like series objects or NumPy array. And then you can like carve out different pieces of data frames in various interesting ways. Okay, so let's keep this on the screen here. So if I wanted to get out like the one of the columns, then I can use square bracket notation. So like let's say I want to get out the area, that'll give me a series object with the areas. And then I can do the same thing with population. If you want to get out the rows, it's a little trickier. So this will not work. This will give us an error. And if you think about like why, the square bracket notation is reserved for columns. And so in principle, you could have a column and a row with the same label. And so if I use the same syntax for rows and columns, how could pandas know which to refer to? So the way you refer to rows is using, well, there are a few ways. One is to use loc. So .loc is, well, it's like you can think of it as like a thing, it's a thing that can be indexed using square bracket notation. And so you could get out like the row of this data frame for California by using states.loc of California. And then if I wanted to get like California and Florida, I could use this, this notation here. If I wanted to get everything from Texas to Florida, I could use the, Texax. I could use the colon notation, like slice notation. Then I could even get like I could double index the rows and columns. So I could index the rows. This gives me a data frame. Now I can say, well, I just want the areas. That'll give me these states in this column. Okay, does that make sense? The other useful, so sometimes you know the labels of your rows and sometimes you might not. So another useful way of indexing out the rows of a data frame, let me just clear this up so it stays on the screen, is you can use a different indexer called iloc, like indexed location. And that works more like a NumPy array where you could like get out the second row to the end, or the fourth row. So you refer to .locs using the index itself, and iloc refers to the position in the index itself. Does that make sense? So like, in other words, the like element number. So 0 refers to like the first row. This would refer to the first and second row, etc.
I might have just, sorry. I might have just missed this, but can you use iloc for rows or just for columns?
So
sorry,
iloc
for
only
column.
works. You cannot use it for just columns, but yeah, you can't use it. Let's see what this does. No, yeah, there's no good way to that I'm aware of let's see. It's a good question. We could pandas index column by number. Let's see. Oh, does this work? I wouldn't think this would work, but maybe. No. Yeah, so the way that I usually index out columns with number, if I need numbers, is a little bit of a hack. So you can say states.values and then all the rows, and let's say I want the second column. You could do this, and I could like make a new data frame. It is kind of a hack, but where this is the data, the index is the index of the original one, and then the column is we could just say it's states dot value or states dot columns of the thing we selected out. That will, so if you don't know the column name, you can get the column name by states dot columns of that index. And then essentially, so I'm like carving out the NumPy array that underlies it and then using that to make a new data frame.
Can you just do, instead of like using the name of the column, can you put in that whole states.column 1 and use that to get like the index? Because that'll return the name, right?
Oh yeah, yeah. So you could just say, that's a great idea actually. So you could say states of states dot columns of 1. Yeah, that'll work. That's a much better, that'll give you a series object, but that's actually a nice way to do this. I wonder if you could just do this. Yeah. So you could just cast it to a data frame. That's way more elegant, actually. Cool, good idea. Okay, cool. Oh, yes. It's also, another really powerful thing you can do in Pandas is modify data frames. So here is one way of adding a new column to a data frame. So let me just do this. We can look at states. So I'm creating this new column density that takes this is a series, the population column of the data frame, and divides it by the area column of the data frame. And then the density would be like, people per square mile or something like that. So you can see that like the columns act kind of like NumPy arrays where you don't need a loop to fill in all the values. You can just, use this divide syntax just like in NumPy, and Pandas knows to interpret that as like, okay, you divide the population of California by the area of California. And then the answer is going to go in the density column and the California row, etc. So it's like everything is kind of nicely cataloged and aligned. Okay. Okay. Oh yeah. Let's say there's a birth. So if you notice, like, okay, the population of California is here. We could add 1 to it by saying, by using this loc notation. So this refers to the row, and then the second element refers to the column. And this says, take the current value of the California row and the population column and set it to itself +1. So we went from, ending in 522 or 521 to 522 by adding 1. You could also notice like nothing else gets updated unless we explicitly tell it to. So the density column was computed based on population and area, but its values are not changing unless we explicitly updated it. Okay, how you feeling? Okay, so I thought we could play around with a actual little data set here. Let me paste this in. Okay, so let's read in this data set. Oops. Okay. Clear this up. Okay, so here's what the data set looks like. So it's got 398 rows, 9 columns, and here's a summary of it. So it's like this data set stores the different properties of 398 models of cars. This is like a classic data set for like data science libraries to like show that it works. Okay. Yeah. So, well, let me maybe walk through a few of the ways that I would approach kind of trying to understand this data set. So one really useful function is called head. And that prints out by default the first 5 rows of the data frame. So, you know, if the data frame has hundreds of rows, it's going to be kind of unwieldy to scroll through. But I could get a sense of the first few entries by using the head function. And then if I pass in a number, it'll like, instead of printing out the first 5 rows by default, it'll print out that number of rows by default. So if I just wanted the first 3, I could do this. And then tail looks at the last, that number of rows of the data set. And the default is to look at 5 of them. Another useful thing is to use a function called describe. This basically just prints out a bunch of like a kind of a summary table or a report of the data in the data frame. And one interesting thing is this is actually also like that report is also itself a data frame that you can then like access. But if you wanted like, you know, okay, how many things are there? Well, that's the count row. If you wanted the average values or the standard deviation or the minimum and maximum or the like, you know, 50th percentile would be the median, but you could get the 25th or the 75th percentile too. So it kind of tells you for any numerical columns in here, ignoring missing entries, what are the, you know, how does the data set look? And then there's like a gazillion like really useful functions for like carving up a data frame, reorganizing it, like, you know, selecting out a particular piece, dealing with missing data. Like if you have a time series, like, you know, computing averages in a like sliding window of times that you increment by 1 each time. You can connect data frames together. There are tons and tons of like really useful functions. It's like, it's essentially not practical to go through each in turn because there are hundreds and hundreds of them. But I thought that I could say like kind of a summary of how to think about pandas, or how I think you should think about pandas. And then I thought we could like dig into this data set a little bit and, you know, just make up a few analyses and, you know, I can show you how to do different things. Okay, so the kind of take homes here that pandas is a really awesome way for organizing and manipulating data. For me, the most useful thing, so essentially what pandas adds over NumPy is these labeled rows and columns. And the reason that I think that's so powerful is it makes it a little harder to like analyze your data in the wrong way. So let's say you have like stock market data from like, particular set of years or days or whatever. And you want to combine that with stock market, look at a different data set. If you had the, data sets organized in NumPy arrays, you could like add those together or, concatenate them next to each other or stack them on top of each other. And NumPy will allow you to do that as long as the dimensions match up. It doesn't really care what the days mean or what the columns mean. Pandas will complain or will handle the labels in a nice way, so that if you have like two tables you're combining, it'll look at the labels and it will only combine things whose labels are compatible with each other. So it like takes into account, okay, if you're exploring a time series, but you don't necessarily have all the observations for every piece of your data set, when you plot them, you want like the x-axis that's plotting time to be correct for everything you plot. You don't want it to be like, the first thing goes back to 1970. The second thing starts in 1993, et cetera. But like when you plot them, it all starts the x values at the same place. Or like if you have like stock 1 changing over time, you don't want to treat that the same as stock 2 changing over time, even if stock 2 only appears in one of your data sets. So it's basically useful as a bookmarking tool and for like preventing you from accidentally combining the wrong things or like doing bad things with your data set that kind of are invalid operations. So in order to do an invalid operation in Pandas, it's a little bit trickier than in NumPy. And basically, as you learn these kind of Pandas functions for carving out a piece of your data frame or adding a new column to your data frame or changing the values, the more of these functions you learn, the more efficiently you'll be able to work with different data sets and do your analyses that much faster. Also, the more you learn NumPy, a lot of NumPy's functions either just work by default in Pandas or have analogs in Pandas that you can manipulate. So that's really useful too. Okay. Okay. So I thought we could, take this data set and then, I don't know, let's try to do some stuff like, can you think of any like analyses that could be interesting? Or so we have like miles per gallon, number of cylinders of engines. Don't know what displacement is, horsepower, the number of horses that live in the car, how much the cars weigh, how fast it can accelerate, the year, I assume after 1900 or something like that, the country of origin and the name. So what sort of, like, if someone was like, okay, oh yeah, Nathan.
Like maybe you could like try to find like the correlation between two of the different variables.
Yeah, let's try it. So what should we try to correlate?
We could do like weight and acceleration, because like we already kind of know that there's a relationship between that and like physics, but like kind of see.
Yeah, great. Okay, so let's carve out just the weight and acceleration columns. Well, one thing we could do is just plot, let's see. I'll use Seaborn. Well, oh yeah, we can do let's see. Okay, we'll get into this plotting library, but maybe just to get us started, we could say, let's see, so we could have weight on the x-axis and acceleration on the y-axis. Let's see what we get here. Okay, so there's some link here. So that makes sense. So as weight increases, acceleration decreases a little bit. Maybe we want to know like the correlation. So, oops. So let's see. We could compute the correlation between the weight and let's see if this just works. Okay. So what this is doing is it's correlating. So you pass in two things, two series, and then it correlates like the thing with itself, or the first thing with itself, the first thing with the second thing, that's this column, the second thing with the first thing, which is the same, and then the second thing with the second thing, which is a 1. But the interesting, so the off diagonals are the same and the on diagonals are the same, but the interesting thing is there's a correlation of negative 0.417 between weight and acceleration.
Is there ever an instance where like the diagonals are not the same?
Nope, not if you just pass in a series of things.
Okay. So they just put all 4 things just to like be thorough?
Well, you can do fancier things with this function that can, like you could correlate. So we could pull up the documentation for this function. Let's see. This is kind of inscrutable. See if the manual has a better. Okay, yeah. So you could pass in one set of things X and one set of things Y, and a different set of things Y. So we passed in like column vectors for X and Y, but if we passed in matrices, I think what it'll do is it'll correlate the corresponding entries. Let's see what it does. Let's actually try this. I'm curious. So let's say we wanted to like if we wanted to do we could correlate. Well, I don't know what displacement is. Acceleration. Okay. Acceleration and displacement. Oops. Okay. And then we could correlate that with weight and horsepower. Okay, so these are now 2D things. So let's see what happens if I correlate these. Okay. Oh, that's silly. I guess they're like are these all just oh, did I pass them in the wrong way? Okay, I passed them in the wrong way. Okay, let me unpack this. The dot T here, change it, it's called transpose. It changes the rows to columns and the columns to rows. And it looks like NumPy, if you pass in matrices, it's correlating the like across the rows. And so, so this must be the correlation of, oh, I don't know. Well, what are the values here? Oh, there must be missing entries. Let's see. It must be that some of the horsepowers are not filled in, but this is computing the correlation between like weight and it must be itself, and then weight and horsepower, weight and acceleration is this. Yep, that's the same numbers before. Weight and displacement is this. Horsepower and everything else is just all mans. So I guess we're not getting ones along the diagonal if we get bad data, missing data. Let's see. Let's see. Otherwise, oh, if the due to floating point rounding errors, you can sometimes get non-one diagonals, even if you're correlating something with itself. And you could get things bigger than one. That's silly. It almost never happens. Oh, okay. I guess NumPy is clipping. Oh man. Oh, you know where you might not get a one is, so you could get a -1 maybe if you had imaginary numbers. That could be interesting. I guess like correlations are, so if you had a time series where the standard deviation is like the imaginary number I, then in the correlation formula, you're dividing by the standard deviation. There's like a piece where you divide by the standard deviation. So if you were like correlating a real and a complex time series, you could have a correlation of, or like you could have that dividing number be -1. I wonder if you could get a correlation of -1 with between a time series and itself if it was imaginary. Maybe. That could be weird. It'll never happen in I don't think it'll ever happen in this course. We don't really work with imaginary numbers. Okay. Interesting. Okay. Yeah, what else should we try? Anything else you want to try?
Are we going to do like sort of more about how to do graphs on a different day, or is that what we're doing now?
No, we'll do that on Monday. Yeah, so we'll unpack this on Monday.
Okay.
Yeah, I kind of cut ahead here.
No, that's, yeah, I was just curious.
Yeah, there are lots of cool things. Like I could color these by, like, I don't know, model year. And then I could have like the size be based on horsepower. Did I spell it wrong? No. Horsepower. Oh, must be. That works. Let's see. Let's see. Well, I thought it would be size. Interesting. Well, anyways, can't remember what the way to change the marker size is. I'll have to look that up. We could have like, I wonder if you could do this. No.
I tried it out. It's OLS. We'll give you a line.
Oh, ordinary least squares. Great. That's cool. Oh, that's nice. Yeah, cool. Oh, and that function is depreciated in this. Great. Cool. Yeah. So there you go. Cool. We could also start to like, let's see, cars. We could like select out cars whose model year is like within a certain range. So let's see what the unique values are. Okay, so it looks like they're all between 1970 and 1982. But let's say I only want cars from the 80s. I could say like cars dot query and then model year greater than or equal to 80. Just kidding. That will do it. And then like now it'll only contain things that are greater than or equal to 80.
What about
that-
like, sorry.
No, yeah.
I was just gonna ask about like statistics, like mean, median, mode, and how you can get those from like even just like if you're still in the 80s, can you like just get that?
Yeah. Oh, it's like what if I wanted to compute this just for cars in the 80s?
Yeah.
So I could do yeah, so I mean, there are no cars from the 90s or above, but so well, let's unpack this. So this gives me a data frame. And then I could just say like describe of the data frame, and that will give me the statistical summary.
Is there a way to just like return like just the mean of like the horsepower or something like that, or the weight?
Sure. Yeah, there are a few ways. So first of all, we could say like describe, and then we could get out the mean row by saying loc of mean. And then I could select out horsepower. Or we could say, so this is our whole table. I could select out the horsepower column. So that's a series object. And then dot mean, I believe, gives me the mean, like the average. You can also, let's see if this, oh, okay. So by default, Pandas, I believe, ignores missing values. NumPy does not. So these are the values. So if I get the NumPy array that corresponds to this, you see some of these are nans, which are missing values. So if I used NumPy to do the mean, it would just give me a nan, like not a number. So there's a secret, or not a secret, an additional function you have to use to ignore nans in NumPy called nan mean. But I guess Pandas uses that by default. If you had like multiple columns, like horsepower and miles per gallon or something like that, then you'll get out a series object with potentially multiple entries in it. So this will compute the mean horsepower and miles per gallon for cars and manufactured in the 80s. Yeah, so there's like a, where you could do the standard deviation, the minimum, the maximum, the median, etc. Pretty much any, you could do the sum, products, any kind of standard math function you can do. Count, mode. That's weird that gives you a data frame instead of a series, but a little Python or a Pandas bug. That's interesting. Yeah. Cool. Okay. So the way to it's like if someone teaches you it gives you like a dictionary of let's say the Oxford English Dictionary, and gives you the dictionary definition of every word in English, say. Now you have all the technical information you need to go out and write a Shakespearean play, but it's not gonna get you fully there until you actually start to put this stuff together and use it in practice. Not that Pandas is as complicated as a self-contained language, and not that NumPy is as complicated as a self-contained language, but it's not typically useful to just memorize all the functions in Pandas. What's useful is okay, how can I look up how to do something, which probably initially will be asking questions on Slack or in class or over email or whatever. So you'll say, I have this weird data set in this strange format. How can I convert it to another format or get out some value or range of values or set of values? And then you'll learn how to do it in that one case. Maybe you'll learn some new functions, and then some of those will apply to the next thing you want to do that's confusing. Some won't, and you kind of build up that way. So that's how your kind of fluency with Pandas and Python and NumPy and all the other libraries you end up using will kind of go, is my guess. That's how it usually works. Okay. Okay, so we're at the end of class, so I want to be respectful of everyone's time. On Monday, we're going to go over some data visualization tools. And then after that, we're going to get back into data stories with assignment 4. So we'll do some brainstorming, and then we'll have an extra piece where we go over some implementation details. So that'll happen on Wednesday and Friday next week. And then on Monday, you'll actually, a week from this coming Monday, you'll do your assignment for data stories. All right. Have a great weekend, everyone. See you on Monday.